Hello, class. This is actually my second lecture for the day, but it's late. It's like 8 o'clock at night, so this will be the last one too. But after 4 lectures yesterday, I wanted to at least do 2 lectures today. And it follows on from the earlier lecture that we had today on coaxial cable. So this is really the coaxial cable example. But part B, which would be the propagation constant. So we're going to use those things that we've already gotten. So let's write those down. I had R prime was 1.03, and of course this was for a frequency of 500 megahertz, right? Yeah, I'm not getting these those acetone pens. Those aren't working out too well. Anyway, you don't get much when you buy some, like 20 of them for $2 or something. I can't remember what I paid for them. Anyway, let's go back to this. So R prime for, and this is for 500 megahertz, was 1.03 ohms per meter. We had the capacitance per unit length was 68.3 picofarads per meter, I think, something like that. And then the inductance per unit length was 384 nanohenries per meter. Right, so we had those three, and then also had R sub S, but you can refer back to that if you want to. You know, I did not give you the equation for G prime because G prime, as I mentioned before, was going to be 0 mhos per meter. And we don't have to really worry about G in any of the calculations that we're going to be doing, because the one thing, oh, and isn't it great? Now I've changed the focus, and I've changed this, and I figured it all out finally, and I'm in like 40 lectures in. But from now on, and for, I don't know, anybody in the future, I'll at least know how to do it so that it stays in focus and everything. Look at that, no focus change, everything's good. Sorry about that. Anyway, let's get back to this. So when we look, oh, you know, the equation, I can actually give you the equation for G. G would actually, the equation for that is 2 pi times the conductance of the dielectric. That's the conductance of the dielectric, which would be 0, right? I mean, foamed polyethylene, how much current flows through plastic? Not much. So that's going to be 0. And then that would be over the natural log of B over A. And of course, since that's 0, then this is going to be 0, and we don't even have to put equal sign there. So I think everybody can see why that is the case. And I'm just going to block these off so that we know that we had those as a given for the problem. And then let's look at the propagation constant. I hope everybody can hear me okay. All right, so now when we put those in, and I'm going to do this in a couple steps here so that everybody can follow me. I have, let me do it this way. I have 1.03. Let's write that equation out first. The propagation coefficient is going to be R plus J omega L times G plus J omega C, right? Does everybody remember that? That's what our equation is, R plus J omega L times G plus J omega C. And we know what omega is. And let me just finish this up, because what does this equal? This equals alpha plus j beta. The propagation constant is a complex constant, and alpha is going to represent my attenuation in Neppers, and beta is going to represent my phase shift in radians per meter, right? So this would be Neppers per meter, radians per meter. I'm going to talk a little bit about a Nepper for a second. I'll write that down here, like you know, 1 Nepper. So we can talk about that in just a second, so I won't forget. Anyway, let's get back to this. So I have R plus J omega L. So this is going to be R, and of course that's R prime plus J omega L prime, G prime, C prime. They're all prime. So 1.03 ohms per meter plus, so that's R, plus J times omega. And what is omega for 500 megahertz? That's 2 pi, right? 2 times pi. Well, 2 times 500 megahertz is 1 gigahertz, right? And then pi is 3.14. So this would be 3.14 times 10 to the 9 radians per second, right? Let's not forget what omega is. Omega equals 2 pi f, and that is 3.14 times 10 to the 9 radians per second. And that's what I've got here. So J times omega L, 384 nanohenries per meter, right? And then I'm going to multiply, I'm going to take this, so let's put, you know, a bracket around that, and I'm going to put a brace around here, you know, just that's the hierarchy. All right, now we're going to multiply that times G plus J omega C. So G is 0 mhos per meter, right? Plus J omega C, which is J times 3.14 times 10 to the 9 radians per second. You know, I could have done this more simply, but I wanted you to see how I put all these numbers in, and then 68.3 picofarads per meter, right? And okay, that's the second part. And then here's my braces, because I have to take it to the square root, don't I? So I've already done this. I've thrown this in the thing, and I've done the next step. So what we get in the next step is, I'm just going to put the braces here now, and I get 1.03 ohms per meter, right? Plus J 1205. I'll let you multiply all that out to make sure that you get that same thing, ohms per meter, right? And that's multiplied. I should have put parentheses there, but don't worry, I can throw braces in anyway. By 0 plus J 0.2136 mhos per meter. All right, and then let me take the square root of that. I want to multiply that together. What I end up getting there is 257. Oh, I'm sorry, minus 257.4 plus J 0.2200, all taken to the square root. If I wanted to then change that into I'll give it to you in both ways. That would be 257.4 at an angle of 179.95. That would be the phasor form of that, right? This is the A plus JB complex number form. This would be the phasor form of what's inside the parentheses. You see that it's a minus, so that's why it's 179.95. Don't let your calculator mislead you. And so if I take the square root of that, I end up getting 16.03 at an angle of 89.98. I hate to sort of do this. I'm going to put an arrow here showing that I'm going the opposite way of, right? I'll put that there. Although, you know, everybody can see that should really be an equal sign. And then if I wanted to break this down into its two components, alpha and beta, this would be 5.6 times 10 to the minus 3 nepers per meter, right? That's my alpha. Well, now I didn't leave myself enough room, but whatever. Plus J 16 radians per meter, and that's my beta. So let's just put these down here. Alpha is going to be 5.6 times 10 to the minus 3 nepers per meter. Excuse me. 1 nepper we know equals minus 8.68 decibels. And I'm going to derive that. Maybe if I have enough room right here, but that's what it's going to be. And so if I wanted to find out, is that what I got there? 257.16. Yep, no, that's right. Yeah. Let me just do that. What did I get there? 5? Yeah, that is a 5. That's not a very good. Oh, I wrote it up here anyway. So equals alpha. Let's just box that. That's alpha. And then this is beta. And what I wanted to do, though, is to change that into there. And what I end up getting is 0.0486 decibels minus decibels per meter. And what we could say there is that if we want to look at, let's say, kilometers, 1, 2, 3, that would be minus 48.6 decibels per kilometer. Right? Does everybody see that? I forgot to put my timer on again, didn't I? Yeah, I did. Oh, well. I pretty much know 1 page is pretty much what I get for my 35, 40 minutes. So we've got 2 things then. So let's look at beta as well. Now beta is 16 radians per meter, right? Or I could say that it is 16,000 radians per kilometer. Now, what do I mean by these 2 things here? I just want to sort of point them out. Let's say that I have, and I'm sure I've mentioned this, I may have, I may not have, to you before, but let's say that I have a waveform that is attenuating along its length, right? A real. In other words, my real attenuation constant. What does it look like? Well, this is what it looks like, right? My frequency stays the same, but the amplitude gets smaller. So Frequency is the same, amplitude smaller, right? Now, is that the only way that a waveform loses energy? No, it's not. I can also lose energy like this. I can start off, right, with a high frequency, and then I can keep the same amplitude, but my frequency can get longer. Does everyone see that? Because when we look at energy in a waveform is Planck's constant, electromagnetic waveform. As you probably remember from one of the earlier lectures, energy in a waveform is Planck's constant times the frequency, right? And isn't the frequency times the wavelength equal to the speed of light when it's in the air, or equal to the velocity of propagation? You know, like let's say when it's in a coaxial cable. So what I'm saying here is that as the frequency goes down, right, the wavelength is getting longer, but the frequency is getting shorter as this goes out. So the frequency is getting smaller. Does everyone see this? So the amplitude is the same, but the frequency is smaller. And so I'm losing energy by an expansion of the waveform. I hope everybody sees that. Good. Because so many electrical engineers don't even understand that this is an energy loss. They look at this, and they look at it not as an energy loss, but as just an expansion of the waveform. They don't really care. It doesn't really make any difference. It's imaginary, right? How many times have you had somebody talk to you about complex numbers and say, oh, well, we don't have to worry about that part. That part's imaginary. Of course it's not imaginary. That's just a word. It's a placeholder. Of course it has meaning. It means that I'm losing energy due to a displacement of the wave. The wave is an expanding wave because, I mean, I'm exaggerating, of course, but even look over here, you know, and then this one, we all see this and we think, well, that's the only way that we can attenuate a waveform. No, this is attenuation of the waveform. This is attenuation or of the energy in a waveform. This is attenuation of the energy in a waveform, but in a different manifestation. I hope everybody sees that. Now, here's what I wanted to do. I wanted to look at, you know, one Nepper. Now, when we're comparing Neppers, when we look at the definition of a decibel, right? A decibel is 20 times the log to the base 10 of V out over V in, right? That's my decibels. And so now we've got this fall off. What a Nepper really is a fall off to 1 over E of the voltage. So really what I have here for a Nepper, if I wanted to define a Nepper in decibels, a Nepper would be 20 times the log to the base 10 of 1 over E. Okay, let's do that. So 20 times log to the base 10 of 1 over E. Well, we know E is 2.71828, right? So if we take 1 over E, well, let's get E to the X, 1 over E to the X, taken to the log times 20, and that gives me minus 8.686, right? Decibels. So there you go. 1 Nepper, which this is right here. This is what we think of in engineering terms, a Nepper. You're probably saying, oh my God, what's going to come at us next? I've never heard of a Nepper before in my life. But that's what that's the engineering, you know, thing. Okay. Anyway, so we've got these. We see what these are. How many neppers, how many decibels, because we can think in terms of decibels probably easier than we can think in terms of neppers, since this is probably the first time you've ever even heard of a nepper. Now you know what a nepper is. Now you know what the decibels are. Now you know what the phase shift is. Now what I want to do is I want to look at this in two other configurations. Okay, let me just cut this off here so that we know what we already have worked on. I guess I sort of should cut that off there. Now, what I want to do inside the box that I've got left is I want to look at this not at 500 megahertz, right? Let's look at this if frequency equaled 500 hertz. Okay, 500 hertz. Well, if we look at R sub S, right? First, let's go to that. So R sub S equals the square root of pi, that's going to be the same, times the frequency. Well, the frequency is going to be 1,000,000 times less, right? Now that's still going to be the resistivity of the copper signal line, and this is going to be the permeability of the copper signal line. So the only thing that changed in that equation whatsoever for R sub S, and why don't I write R sub S down here for the 500 megahertz. At 500 megahertz, it was 5.63 times 10 to the minus 3 ohms. All right? 5.63 times 10 to the minus 3. Boy, that doesn't look, yeah, you can see that. 5.63 times 10 to the minus 3 ohms. So if it's 1,000,000 different in here, and I'm taking the square root, isn't going to be 1,000 different. So at 500 hertz, which is going from 500 megahertz all the way down to 500 hertz, right? Submarine communication frequencies. Let's see how much further you can go, because look at this. This is for 1 kilometer. That is minus 48.6 decibels. That's quite a bit. Thinking that decibel is in a logarithmic, an exponential scale. So let's go back to this. So if F equals 500 hertz, that's going to take this thing down. So R now, or well, let's just say R sub S, instead of being 5.63 times 10 to the minus 3, it's going to be 5.63 times 10 to the minus 6 ohms, right? And that's going to make R prime equal to 1.03 milliohms per meter. Does everyone see that? Wow, that's a huge difference, isn't it? I've gone from 1.03 to 1.3 milliohms. And then when we look at C prime, that's going to be exactly the same because there's no frequency involved in there, 68.3 picofarads per meter. When we look at L prime, well, that's the same thing, nothing in there, 384 nanohenries per meter in its equation, nothing in its equation that has frequency involved at all at that point. At that point. Now, that's giving us R, C prime, L prime. We know G prime is 0. So that is our givens for 500 hertz, which is 1,000,000 times, not 1,000,000 less, 1,000,000 times less than 500 megahertz, isn't it? So what I want to point out here by using these numbers is let's just look at what gamma now becomes. Because gamma, the propagation constant now becomes 0.00103 ohms per meter, right? Plus J 0.00120 ohms per meter. I'm just putting these numbers in and working them through the same way that I worked them through up here, right? Times 0 plus J 0.21 times 10 to the minus 6 mhos per meter. All right. So when you look at this one here, I've still got the same thing, 0.2136 mhos per meter, 0.21. Now this would be times 10 to the minus 6. And why? Why? Because if you look up here, this has omega in it too, doesn't it? And omega isn't 3.14 times 10 to the 9 anymore. Now omega is 3.14 times 10 to the 3, right? Times 10 to the 3, 10 to the 9, 10 to the 3, that's 10 to the 6. The square root of 10 to the 6 is 10 to the 3. So that's what I've got here now. I think you guys can go back and check it out, but I mean, not check it out. I'm sure it's correct, but you can just put the numbers in like I did up here and follow the equation up here, and you will come to that same conclusion. Now, when I work that out, I get minus 252 times 10 to the minus 12 plus J 216 times 10 to the minus 12, all taken to the square root. And if I do that and take that to the square root, I end up, well, let me write it in phasor forms for everyone so that everyone can see what I've got there. Writing in phasor form, 335 times 10 to the minus 12 at an angle of 135.4 degrees. And I want you to just figure that out. That's a minus, that's a plus. Remember, that's in the second quadrant, right? Everybody can see that's in the second quadrant, and then that's going to take, I'm going to take the square root of that, and taking the square root of that gives me 18 times 10 to the minus 6 at an angle of 67.7 degrees. And if I wanted to write that out in its complex number form, that would be 8.74 times 10 to the minus 6 nepers per meter plus J 15.7 times 10 to the minus 6 radians per meter, right? This here being alpha, well, that's a bad alpha. That's an alpha. And this here being beta, right? So alpha is 8.74 times 10 to the minus 6, whereas up here it was 5.6 times 10 to the minus 3. So alpha is 1,000 times less, almost 1,000 times less. Does that mean it can go 1,000 times farther? Yes, that's exactly what it means. So instead of just going 1 kilometer like this and being at 50, losing 50 decibels, I can go 1,000 kilometers. I can go almost 1,000. Well, let's not say 1,000 because that's 5.6, that's 8.74, but you know, almost 1,000. Let's say 800. I can go 800 kilometers if I broadcast at 500 hertz, and I can only go 1 kilometer if I broadcast at 500 megahertz. Do you see the difference there? Now, also, what I'm and also look here, you can see this has changed quite a bit too, right? Instead of being 16 radians per meter, it's almost 16 times 10 to the minus 6. So this is 1,000,000 off, and this is 1,000 off. So this changes by 1,000,000, this changes by 1,000. So everyone see how they work. Now I'm going to also do another one where I look at a larger coax, a coax that still maintains the same ratio of B over A, but is a much larger coax. And in fact, they're trunk line coaxes that you see every day as you walk by and look at a telephone pole. You look up and you see something that's, you know, much bigger than a coaxial cable hanging on that wire. It's probably about 1 inch in diameter. It's another wire. It's a coaxial cable is what it is. And it's traveling down that telephone wire with all of the other power lines and everything else. But it's about 1 inch in diameter, a little bit more than 1 inch in diameter. That is a coaxial cable. It's a 75 coaxial cable, but it's a trunk line coaxial cable. And that's what I want to talk about in the next lecture. Okay, I hope everybody is seeing not only how we figure out what R prime, C prime, L prime, G prime are for the, did I not draw the communication circuit on here? I didn't. There's no place to draw it either. I guess I'll have to draw it right here. Always remember your communication circuit. All right. See you at the next lecture.